Okay, so let's talk about circular motion at constant speed. So let's imagine that we are in the x, y plane and moving on a circle that looks like that. Okay, so the object could be here, and it's going around at a constant rate. So the distance from the center, which is the origin of the xy coordinate system, is, say, r. That's not going to change, but the angle here, theta, changes with time, and it changes at a constant rate. So let's look at the position of the object. Let's figure out the velocity and the acceleration, and let's notice a number of things about this special type of motion. So what is the x coordinate of the object? So when the object is here, the x coordinate is clearly capital R, but when the object is here, the x coordinate is 0. So Pythagoras' theorem applies here, and we can notice that the x coordinate is r cosine of theta, and that belongs with an I hat, right? Because cosine of 0 is 1, and so we get r, and when theta is pi over 2, or 90 degrees, this is 0, and x becomes 0. What is the y value, right? The y value, that's just r sine of theta. So we have r sine theta, j hat, because that's the y component. Okay, and that's the position of this object. But of course, the angle theta is actually changing with time. And so when we take derivatives, right, the velocity v, which is the time derivative of that, we can write this as dr dt, and that gives us, right, what's changing with time? Theta. So we have to take the derivative. Everything else is constant. The I hat is constant. The capital R is a constant. But theta changes with time. But we first have to take the derivative of the cosine, which gives us minus the sine. So we have an R times d theta dt times minus the sine of theta I hat. Okay, that's what the x component looks like. It's r times d theta dt times minus sine theta. When we do this here, we get the cosine of theta times d theta dt, so we have a common d theta dt times r that we can pull out, and we can write this as the cosine of theta j hat. And so notice that the velocity has a value which is always constant in magnitude, so its speed is constant, theta dot d theta dt is constant, r is constant, but the direction is changing, and the acceleration, which is dv by dt, or d2r by dt, involves the derivative of this object, and this quantity is just a constant, so we get there's an overall minus sign, theta, d theta, we get a d theta by dt squared, so we actually square this because we have to take derivatives of these two functions. That brings out another d theta dt, and it turns the minus sine theta into a cosine of theta, actually into a minus cosine of theta, and so we pull that minus sign out, the cosine, the derivative of the cosine gives us the minus the sine, and so we can pull that minus sign out and make a plus here. Here we have an I hat, and here we have a plus sine theta j hat. Right, this could be meters, meters per second, meters per second squared. So that's the acceleration. And so we can notice that the magnitude of the velocity is just, right, so we have sine squared and cosine squared. Those add up to 1. They don't add anything to the magnitude. The magnitude comes from this part, so it's just r d theta by dt. And that's some constant quantity, and the magnitude of the acceleration is r d theta by dt squared. We can also write this using this, r d theta by dt is v, and so we could write it actually as v squared, but we have a missing r squared here, and so if we say that this is proportional to v squared, then we have an additional factor of r, so we would have to divide by r. So the magnitude of the acceleration is related to the velocity according to this expression. So this is the magnitude of the acceleration, and now notice that if we're here, say, let's write the acceleration, let's notice that the acceleration at theta equals 0 involves sine of 0, 0, and so we only have an x component, and cosine of 0 is 1, and so we have a negative I hat. There's some value, which is actually this, but the point is that the direction of the acceleration there is that way. Let's go over here. Let's see what the direction of the acceleration is when we're here. Well, we have pi over 2, so this disappears, and we have this going to 1, and so we have negative the same quantity. It's in magnitude this, but minus j hat, so it's pointing that way. And if we go here, we can see that the angle is 180 degrees. This goes to negative 1, and this goes to 0, and so we end up getting a positive I hat, and so we're this way. And when we're here, we can think of this as minus 90. The x component disappears, the cosine of minus 90 is 0, and we have this, which gives us a minus 1, and we have a minus sign here, so we have a plus, and therefore there's a plus j hat component. It's not surprising that if we looked at it in different locations, we would get vectors, unit vectors pointing this way, and magnitudes for the acceleration of v squared over r. So the point is the acceleration is always toward the center for circular motion. So the two things that we care about are, one, that the magnitude of the acceleration is v squared over the radius, and two, the acceleration is always toward the circle center.